You're mixing it all up.
Okay.
What did I say? I don't even know. I said, we don't have to, but we would. We don't need to, but we would like to. Yes.
We don't need to, but we would like to.
Do you want to write that down?
Yeah.
We don't need to, but we would like to. Yes, you did. Okay, can you write this down? Einstein's equation.
Nice.
Complicated. You used to write them at the end of the lesson.
Oh, Einstein.
You know Einstein?
Yeah. I know the picture.
The picture. Oh yeah, that's what you studied. Yeah. What grade did you get for that?
Don't know. You don't know?
You don't know it yet?
No.
Sure.
What?
No.
You? Oh, no, we don't.
Maybe they don't. Alright. Did you write this down, Yusuf?
Yeah.
And Andrew, is he alive still? Is he still producing carbon-14 or is it decaying now? It's decaying?
For the carbon-14, you've had more carbon-14 in your lifetime than us.
Yeah, but it's proportion. It comes from the food you eat. So, for example, if 1% of the food you eat has carbon-14, then 1% of your body will be carbon-14 because your body is made from the food you eat. The parts of your body come from the food you eat.
But then you eat more food.
Yeah, but it's no.
What
Do
you mean? He eats more food than you.
No, it's a percentage. It's a percentage. Like, for example,
I really want this.
your body is built from the food that you eat. If 1% of your food is contaminated with carbon-14, then you will be 1% carbon-14. Yeah, it's a proportion. It's a proportion, yeah. Okay. Because the mass of a proton and a neutron are so small, we do not use kilograms because that is too big.
Wow.
Or even grams are too big.
Milligrams.
Or even milligrams. We use a smaller unit. A unit called atomic mass unit, the AMU or the U. And the definition is 1 AMU is this. Good news for you. This is on your calculator. A constant U.
You have.
So 1 electron is 1 atomic mass?
No.
1 proton is 1 atomic mass?
Roughly.
Atomic.
1 neutron is 1 atomic mass.
1 neutron?
Yeah.
Because it sounds like you said 1 Newton.
No, 1 neutron.
Yeah, roughly.
Don't know how does this number come? That's English. Where did this number come from?
How did this number come long time? Why? Explain.
No, where does the number come from? Like if it is the mass of 1 proton, okay, makes sense. But it's not. Why means
Good question. I don't know if I have to check, but because you define the mole using carbon 12, I don't know if this is like 1/12 the mass of carbon 12 or something. I don't know. No, I don't know.
But it does make sense that.
Yeah. Well, logically that would make sense to me, but I'd have to look it up. It could be a different reason. It could be like, well, that's because just the number Einstein picked.
I saw the website that you read physics things from.
Yes.
Physics answers for dumb questions or something.
Not this website, but go on.
What's it called? What's the URL?
I don't know. I read a comic, XKCD.
Yes, this, no. Online. You had it, you opened it on the cab computer and you left it there one day.
Oh, maybe that's just what I got when I Googled.
Took a picture of it.
No.
No, what I discovered was, there's an article that's like 2-3 weeks ago
Yeah.
about the lens thingy, where you told me that you
Oh,
can-
yeah, I remember that, yeah. That was on that website?
Yeah.
Ah, no, that's not where I got that from. I got that from a different website.
was like, this is where he gets his information from.
Yeah, before I go into class, quick read of Physics for Dummies. Okay, I'm ready to go. The mass of one proton or one neutron is about 1 AMU. Yes, it's on the calculator.
XKCD.com.
Yeah. Now, look at the following nuclear reaction. What's happening here? Can you describe it? Hydrogen 1 plus. Guys, come on.
Reacts with lithium 7.
Don't use such disgusting chemistry vocabulary, please. It does not react with it. What's the verb?
Radiate.
Better, but not there. What's the verb here for the plus?
Contaminate.
Okay, no. Attaches. So hydrogen 1 attaches to lithium 7, and what is formed? 2 helium 4. Is this equation balanced? Let's check. How many protons on the left? 4. And on the right? How many nucleons? 8. And on the right? 8. So it's balanced. It's balanced. Okay. I want you to do a quick calculation for me. The mass of hydrogen 1 is this, AMUs. This is it for lithium. Can you tell me what the mass on the left is, please? Can you write it down? The mass here. Did you write it down? Go on. I want the mass on the left. You don't have to, but I want you to. Please do it. Yusuf, do you have it? Yeah, what did you get then? 8.023. Good. Now, keep that number in mind. What's the mass on the right? Can you calculate the mass on the right, please? Well, it's pretty clear. What is it? 8.004. They are different. Which side is bigger? The left. What's going on? Any ideas? Not the case, because all the mass is here. The system is closed. Nothing escaped. It's closed.
There's 2 heliums.
Yeah, but the mass on the left and the right, they're different. You have less at the end than at the start. Possibly, but the system is closed, so it's all contained. I'm not missing anything.
There are things that we're not measuring?
No. Mass does not just disappear.
Wait.
Or
0.115. Yes.
does it?
It decreases by 0.01.
Yeah, it decreases by 0. Yeah, small amounts. So what's going on here? Can mass disappear? Or maybe it became, as Faisal said and other people said, maybe it became something else. Well, this experiment was done by Cockcroft and Walton. They fired real mature, Faisal, real mature. Created by, this experiment was done by CMW.
Okay.
And they were testing a formula Einstein had. They wanted to see if this formula he claimed was true. So they fired hydrogen at lithium and measured the mass afterwards. And they didn't just decide to do this experiment, they were trying to prove a formula Einstein claimed was true. And that formula Einstein predicted was that when atoms combine, there may be mass that appears to be lost, but it was not lost, but rather converted into energy.
What?
Mm.
You can convert mass to energy.
Correct. And not only that, I can tell you how much energy per mass by using this formula. Dun dun dun. Or as commonly written like this. No difference, it's just symbols difference. You've all seen this formula before. Now you know what it's for. It's working out the energy created from the destruction of the mass.
How do you do this? I'm doing that.
You just need a hydrogen gun, like fire hydrogens at a lithium's target.
But then the first thing you ever said, that physics
No,
is
let's say,
based on
I want
energy cannot
to
be
destroy him and turn
created
into
or destroyed.
energy.
Yeah, energy cannot be created nor destroyed. So you haven't really, I know I used the word created, but you haven't created the energy, you've converted it from mass. Which means mass is a form of energy.
Yes. So you mean I am energy?
Technically,
Too
yes.
much energy.
Oh. No, think about this. You are saying,
Yes?
right now, maybe 10, 20 years from now, they will create a machine that can change me from this human form to another type of sound energy?
We're technically potential energy.
Yeah.
Firestorm.
Yeah, the future is sooner than you think. No, yeah, it is possible if you can destroy the mass to convert it into energy. I shouldn't really use the word destroy. You're not destroying the mass, you're converting the mass into energy. Well, we have devices that do this already.
What?
I will be a fire next.
Would you like to know the device that converts mass into energy?
A calorimeter?
No. Does anyone know the device that converts mass into energy? No? Give you a clue. There were two big ones that landed in Japan.
Atomic bomb.
Yes.
Apple.
What?
Atomic bomb.
Oh,
Yep.
nice.
Oh, is that correct?
Radioactive and stuff.
Yes.
Nice.
Great. I'm glad I had that endorsement. Yeah, we'll actually look at how to do that later in the chapter.
We're gonna learn how to make atomic bomb?
No. Well, I'll talk about it briefly. But I'll tell you how to make nuclear power plants, atomic power plants.
How about nuclear bomb?
I think that make sure we're not.
We'll mention the bomb. So can you note Einstein's formula, please? Did you write it down? Yep. Did you write this down?
Yeah.
Formula? Okay. So let's calculate how much energy we get. I think, Yahya, you already had the mass, didn't you? What was the last mass?
The last mass.
Can I have the calculator?
0.013.
8.004 minus...
1119.
Oh, sorry, you're giving me the final answer, isn't it? 0.019. So the last mass was 0.019 atomic mass units. So then the created energy...
It's 0019.
No, I think this is right.
You add the masses and then you divide them by 2.
No, you subtract the masses. How much is lost?
Yes, but then to find what's on the other side.
No. Just add the mass here, and subtract. You're looking at the difference between the left and the right.
How do you find the mass on the right?
You take the mass of this and multiply it by 2. Okay. 0.019 times U times C squared. What did I say the U was earlier in the lesson? 1 point times 27, wasn't it?
Yeah.
And then 3 times 10 to the 8th squared. I got this number. Yeah, I think so.
This is the amount of energy that we would produce if we convert just this mass to energy.
If you fire one hydrogen atom at one lithium atom, you will produce this much energy per collision. This is a huge number compared to the mass. Look, what scale is the mass of the atom? 10 to the minus 27. What scale is the energy? 10 to the minus 12. Let's put this in a better context. Let's imagine I had 1 mole of this. How big is a mole?
6 times 0.3.
10 to the 23. 6 is mega, 9 is giga, 12 is tera.
Yeah.
So 1 mole of this, which isn't much, it's only like going to be whatever, couple of grams, can produce a terajoule. Yes. It's a lot of energy.
A terajoule.
A terajoule.
So, like that's an explosion.
Yes, pretty much. So can you see how much energy is stored inside of mass? It's huge. It's huge.
But what's stronger? Atomic
If I
energy or
explode,
bomb?
I can destroy this whole universe.
Maybe not the whole universe, but at least the Earth. So that's something.
I'll explode in the sun and take the whole universe.
Yeah, but just be careful
The
about
whole galaxy.
be careful about making statements about I'll explode in public. Just FYI. Just be careful. Alright.
I have nothing to do with that. I do not condone that.
Okay. Now let's have a look here. Here is the mass of a proton. A proton is made up of just hydrogen. Hydrogen is just 1 proton. What's helium? 2 protons. Can you tell me what the mass would be of each? 1 proton, there it is there. Can you tell me what a helium-2 would be? A helium of 2 protons, what that would be? Should be twice this, yes. So can you just write down what that number should be?
2.014.
And they should go up to 6 now.
32.
Okay, do you all have that on your calculator? Yes? Florian, do you have it? Why not? Multiply this by 2.
She's asking why too.
Because we're going to look at helium in a moment. Yeah? Okay, hold that there. The mass of a neutron is this. The mass of 2 protons and 2 neutrons together. Let's calculate that. So you have there 2 protons. Can you add on 2 neutrons? 2 of these as well, please. So does anybody you have that on the calculator? Yeah, good. Now hold that there. 2 protons and 2 neutrons, what is that?
Helium.
Helium and also alpha particle. Yeah. If you add the masses together, did you all get this on the calculator? Yeah. But when you actually measure the mass of alpha or helium, it's this, which is less. So now the big question is, when you stuck protons together, what on earth happened to cause them to lose mass?
They lost the energy.
But
No,
they lost
that's
a lot of mass.
Yes, actually, yes, that is a noticeable amount. Any ideas from anybody?
Yes, energy.
Yeah, but what form of energy? Where did it go, George? Oh, you think maybe into giving it a charge? No, the charge hasn't changed, so it's not that. Good try.
When they collide, they make fish.
Yes. Sound energy. It's
No.
Heat.
Radioactive. No.
well, let me tell you this now. What charge is a proton? And the other proton? So when you
Ionizing.
right, when you put 2 protons together, they attract or repel. So how can they stick together if they're supposed to repel? No, there must be some force, some energy that can hold them together, even though they're repelling. Where did it get its energy from to hold them together? It took it from its mass. So the reduction in the mass was to give the atom energy to hold itself together. So this is missing This is called, the term for this, mass defect. It's the knockoff version of the game Mass Defect. It is the missing mass. Can you write that term down? Mass defect.
Simply means the missing mass.
Correct. Yeah. Is that Vietnamese? Okay, continuing. So, the binding energy of an atom is the energy required to hold the nucleus together. Where does it get this energy from? It gets it from the mass. The energy E is equal to the same formula, mc squared. Whereas what do you think the m is here? Yeah, the mass defect. Okay, please note this. Wow, no, that's true too. Okay, please write this down. Do I still have enough energy? Oh yeah, okay. Can I continue? Yusuf, you wrote all of this down?
Yeah.
Your superpower is speed writing, is it?
Because it's mass.
And his is speed sleeping? Yeah.
This is also
So, that last sentence is interesting, and this energy you calculate is the energy used to hold it together. Therefore, that's actually how much energy you would need to separate the protons from each other. And because this is a big number, it means separating protons is actually very difficult to do.
which is a nuclear bomb.
Yes, it is.
But which one is more, and which one gives out more energy, an atomic bomb or a nuclear bomb?
That's the same thing.
They're the same thing?
Yeah, you're thinking of, there's another type of bomb called hydrogen bomb, isn't it?
Hydrogen bombs are crazy.
Yes.
Which ones are?
Nuclear ones are the ones with the most energy. The atomic bombs. Okay. Continuing now. No? I'm sorry for one.
Think about radiation. They do.
Nuclear explosions? Yeah, I think there's some radiation afterwards. Although I have to double check that and find a reference for you. Let me just open up my Fallout game and I'll just to make sure. What? Oh, is there? Oh, thank you. Thank you. Okay. In an earlier lecture, we saw that the weak nuclear force is trying to push apart the nucleus. Newton's law tells us that if the atom is not decaying, then the net force should be zero. Therefore, a counterbalancing force is required. The strong nuclear force is a strong, attractive force which acts only in the nucleus of an atom over a very short range, like 10 to the minus 15. No, slow down, go back. I wasn't ready. Right, over a very short range, like 10 to the minus 15 meters. It is the force responsible for binding between protons and neutrons. So the strong nuclear force is what keeps the atom together. You should make note of this definition. Wait, before you write it down, I should tell you in the exam, what they love to ask is, name 3 features of the weak and of the strong nuclear force. So for example, what is 3 features here from this definition of the strong nuclear force? Number 1, it's strong, correct. That's a good one. And number 2, the range is short. And number 3, yeah, it's an attractive force. Not like that ugly, repulsive, weak nuclear force. Oh, makes me sick.
Don't they both work in a small range?
Yeah.
So which one's small?
I thought, were they both 10 to the minus 15 meters?
So we can't say like the difference between them is the range.
No, because they both operate on the nucleus scale. So that is a similarity.
Then what's the difference? Other than the strength.
The key difference, other than the strength, is one is attractive and one is repulsive.
The strong is attractive. The strong is repulsive. Strong is attractive.
It's easy to remember. Strong people are attractive. Weak people are repulsive.
Look at me.
Yeah, look at this weakling over here. Alright, continue.
What in essence, what they would ask about?
3 things about strong, 3 things about weak.
Oh, what?
Strong nuclear force and weak nuclear force. They're asking for 3 things about it. So look, go on. Number 1, it's strong.
Very small, sharp.
Yeah, and it's an attractive binding force.
It's binding force.
Yeah, between the protons and neutrons.
And that kind of manager at this website.
Manager.
Continue. Continue.
Manager on this website.
Continue.
Yeah.
Go on. Continue on. Yeah, no, I already said that. Right, what is the binding energy of helium-4? So that's actually the one we're in the middle of looking at. We already worked out, if I go back to this slide here, guys, look. We go back here. Oh, how far back do I have to go? Did anyone write it down? The missing energy. Here. So in the helium, how much energy is missing? This much. Can you tell me, sorry, how much mass is missing? This much. Can you calculate how much energy that is? This is the mass.
Which is times out by U.
You forgot the square and you forgot the U.
Yeah.
Yeah, double yeah. What constant is the U?
17.
Okay, and the C should be squared. 4.38 times 10 to the minus 12. Because this is small, what would be a more appropriate unit to measure this energy in? Children. Because the energy is small, what would be a more appropriate unit than
AMU.
joules?
They.
Electron volts. So the answer here is 27.3 electron volts is the binding energy.
How do you convert to electron?
What?
How do you convert?
I can't believe you're asking me. It's divided by E. Can I continue? Alright. Next. So the answer here is 27 electron volts. Okay? Next. What is the binding energy per nucleon? Well, how many nucleons do we have in this helium? 4. So if you divide by 4 per nucleon, it's 6.83 electron volts. Why are we looking at per nucleon? Well, we want to know how much energy per sticky substance there is per side. You know, if I say it takes so much energy to stick 4 things together, I really want to know how much it works out at per thing. Interesting. You can graph this where here is the mass number and here's the binding energy per nucleon in mega electron volts. Oh, I'm sorry, did I say electron volts previously? I meant to say mega electron volts. Now what you notice about this graph is, as we increase in the periodic table, do you need more or less binding energy? You need more binding energy. And you reach a maximum at iron. So iron has the most binding energy per nucleon. What does that tell you about iron? It is the most, yeah?
Sorry.
Yeah, well I mean in terms of a sort of atomic structure, it's...
Strong atomic force.
Okay, can we avoid stating the blank obvious, please? Yeah, go on. Yes, and what about trying to separate it? Yes, you could even say perhaps it is the most difficult atom to separate.
Okay, I just did.
Yeah?
You give us iron, and we spoke about helium before. And then you want us to know that iron is the strongest out of all the elements.
Because it's on the graph. And it is. A great deal of willpower is required on my part.
Yeah. I salute my father.
Yes, he must be a very patient man.
Not very honest.
I don't blame him.
Yeah. I don't do that.
Okay, this is batteries.
This is a wrap up.
What?
See you next.
Yeah, it is a wrap up, but I want to wrap up by just looking at this graph and telling you they will ask you to draw this graph in the exam. So what you need for the exam is binding energy, mass number, as something that curves up, maximum at iron, and curves down. They will ask you to draw this, the binding energy per nucleon graph. Please make a quick sketch and then get out.
Thank you for being so kind.
So, Faisal, what is the easiest atom to separate?
Hydrogen.
Very good. You can read graphs. I shall give you your graph star now and put it on your board. Yes.
On my forehead. It's as big as a board. The first step is accepting that.
Yeah,
That's true. Accept who and what you are.
yeah, first.
Love yourself.
Yeah.
Don't body shame me. I'm proud of me.
Yeah. I treat it like mother.
Yes. Don't body shame him. I mean, that's-
vegan also.
oh no, I won't tolerate that in my class. I can respect the whole no alcohol and pork thing, but no meat whatsoever, I'm sorry, you'll have to leave.
No Indian students before?
What?
No Indian students before?
I don't think you would know about that. Only Hindu, not Indian.
Yeah, Hindu, isn't it?
Yeah.
I don't know if I had anything.
Well, I
to-
think
They have an elephant with 8 arms, like this, like this.
Yeah, Ganesh, isn't there something?
Krishna.
Krishna.
Yeah.
Yeah.
And someone
What?
in Oman, right? In all of the Arab gods. There was
I can close this.